Okay, I'm not gonna write every single definition on the board, but I'm gonna ask you guys what they mean. Pop quiz. Okay, are we starting? Where's Masha? Masha, come back. It's okay, I can start writing, whatever. So this is what we're gonna cover today. Main table of content. Might skip a few like minor details because of the time limit, but let's start with reviewing what a Turing machine is. Anyone tell me?
Yeah, so Turing machine is something like a PDA plus instead of a stack we have a tape where on the tape there's a pointer and that pointer could either move back or forward or change the content of that specific index in the tape.
Yes, so can you give me the tuple mathematical definition of the Turing machine?
Yeah, so there's the alphabet.
Uh-huh.
Q. And
there's an alphabet for your language.
Yeah,
and there's also
the for the tape.
Yes, and you call that gamma.
Gamma. And then I forgot the other two.
You also have a starting state.
Starting state, probably a transition function.
Yes, transition function.
So final states.
Yes, final states. We had like in class definition, it's literally just one single Q accept state for simplicity. You can also have a set of accept states because we're not gonna draw the machine on the exam. You literally just write the pseudocode. So this is just for your information. So in class, we kind of define the accept state, we define the reject state, right? We also have what these two. These two symbols are just for the tape. This is for space. This is for the semi-infinite tape definition. You can literally go infinite on both directions, but this is the in-class definition. So what does your transition function tell you? I think this is kind of important. Like, what's the domain and codomain? Yes?
The domain is it's member of tape alphabet times member of state alphabet, some state times.
We have preloaded the input onto the tape, so you just have to worry about the tape alphabet.
Times left and
right. That's kind of the codomain, right? Yeah, that's the in-class definition. So now we have this Turing machine. I'm gonna skip them like different models of Turing machine you can define. You can go look at your own notes. But yeah, so now let's investigate what a Turing machine can do. Before going straight into what a Turing machine can or cannot do, we should investigate the concept of infinity. So let's start with the remaining principle. Anyone remember what the remaining principle is? Remaining, I think. That's what he called it in class. So, renaming? Okay.
Is this when you simulate multiple tapes using one tape, that sort of thing?
No.
Renaming?
This is comparing set size.
Oh, is it like if you have members of one set and you can like rename them to members of another set, then you can kind of compare their sizes?
It's okay, whatever. So you have two sets, right? If I can define an injective function f going from set S1 to S2, it is injective, then what?
S1 and S2 are the same size.
No.
Wait, no. Then there's a one-to-one function from S1 to S2.
This is one-to-one. There's already like, if given I can define a one-to-one function from S1 to S2, then what is the relationship of these two sets size? S1 is
greater than or equal to S2?
Remember,
Or wait,
a one-to-one function cannot collide on any element in the codomain. Yes?
yeah.
Yes, exactly. And this is equivalent to existing a surjective function because you literally just do the inverse of this function, left inverse of the function, g from S2 to S1, right? Because you have enough elements to cover every element in S1. So S1 is smaller or equal to S2. So that's the remaining naming principle. Okay. So do you guys want to go through an example we went through in class?
Yes, please.
Okay. Let's see. Do you want to do the natural number to rational number one?
That's a good one.
Okay. Great.
I can prove it mathematically later. I think we can do a proof both ways.
Yeah, because they had like a special assignment.
Okay, which one?
It's the cross product of the naturals and integers, producing a set of naturals.
And you want to show an injection.
Yeah. But my proof also shows bijectivity.
Yeah. So
Yes.
mine did as well. So you can
So
show it.
you want me to do this one?
Sure.
Okay.
From the integers to the natural numbers?
Cartesian product of natural numbers and the integers to some natural number.
This is an injection, not a bijection.
It's a bijection. You want to prove the two sets are equal in size, right?
You can.
Yeah. I mean, the other way is super easy. You just set b to 0, right? That's obvious, right? Yeah. If you want to go from a natural number to the Cartesian product, and you want like an injection, you can literally just set like b to 0, a equal to what a, right? So that's kind of really simple. Like injection the other way around is given, but let's prove this direction because this one apparently has somewhat at least the same number of elements as the natural number, right? Yeah, so let's prove that. So anyone want to begin? What do we start the proof with?
So we showed in class that the size of the set of natural numbers is equivalent to the size of the set of integers.
Mm-hmm. Yes.
Because we gave a bijection.
Yes. So, does that help us in any way on proving this one? Yeah, sure.
It helps us because the composition of bijective functions produces a bijective output.
Yes. So we have already a bijective function from n to z, right? Like f is bijective. Now the question is, how do we define a function somehow, either graphically or mathematically, from the Cartesian product to the natural number? Yeah, we do want to do some kind of pairing, but how? Yeah.
If we're doing natural numbers and when you say integers, you mean negative and positive, right?
Yes.
So because we can think about the integers as like two distinct dimensions, like negative integers and positive integers.
Mm-hmm.
We can't treat them as the same.
Mm-hmm.
And then we could, so that's two dimensions. And then the third dimension could just be the natural numbers.
Mm-hmm.
It's kind of like number 1 on homework 4. I don't know if you remember that one. It was like all points in a 3D grid are infinity 1.
Mm-hmm.
And so if we imagine that same 3D grid, but now it represents all distinct pairs of negative integers, positive integers, and natural numbers, and then we snake our way through that three-dimensional graph, then we would have mapping from the set of pairs to other natural numbers.
Mm-hmm. Do you wanna tell us what it might look like graphically?
Graphically, that might look like.
Because every coordinate is discrete.
Yes. So, can we kind of visualize what all the possible A and B are? And then we can just count them, right? We can just label them 0, 1, 2, 3, 4, 5. It would be really easy if we have a pattern that we can guarantee to move to all of the possible Cartesian product. Yeah, triangle, right? Wait, come here. Oh, sorry. You can take that too. Here.
Oh yeah.
Yay! I get to hit people with candies. Let's go. Oh, sorry. Here. Oh, that's mean. Bro, that's mean. Okay. So if you recall what we had, right? If you recall what we had for the rational and natural number, this is literally like the same thing. Except we're directly just taking the Cartesian product, right? Because if you think about this is literally like a possible expression of b over a, right? And that's all the possible rational numbers. So yeah. Yay, we proved that.
When we did the rational numbers in class, trying to find a bijection from rational numbers to natural numbers, did we do the graph as well, or was there?
Yeah, we did the graph. On homeworks and exams, if you could just draw a graph, I think that's the easiest way than doing like mathematical formulas. Yeah. So now let's move on to what Turing machine cannot do, right? Now we get like a taste of what the remaining theorem is about. Let's look at Turing machines. Yay. Yay. So we know that all Turing machines can be expressed in pseudocode, right? And pseudocode is a set of string. It's literally a string. It's a set of characters in some certain order, right? So say this one is like the expression for a Turing machine. And thus we can literally do a bijective mapping from the set of Turing machines to their descriptions, right? We agree that. So we want to study the size of the number of possible Turing machines. Now, how may we use a function from here to here to prove something about? Yes, that's good. Because we want to prove something like the set of all possible languages and the set of all possible Turing machines. We want to prove a relationship between them. Because you remember we proved something through the Cantor's diagonalization theorem that there must exist a language where no Turing machine can ever like represent it, right? Because that's what we're trying to head towards. So right now we're trying to start by investigating the size of the Turing machines. Because if we can get a simpler representation of the Turing machines, like instead of messy strings, if we can literally just label them 0, 1, 2, 3, 4, 5 and count, that would be super easy, right? Yes?
So wouldn't we just use the argument that, okay, well, we know every Turing machine is a string, a bunch of zeros and ones, so it must be infinity 1.
So let's look at the set of strings, right? What is the set of strings? If the alphabet is literally just 0 and 1.
Epsilon, 0, 1,
Yeah,
0,
right.
0, etc.
You have to make two choices, or no, you have to make a choice between two things for each location in the size of the string. So like, as the size of the string increases, you make that choice the number of times as the size of the string. I'm confused. Like string as like a bigger subset is like, or no, as a big subset is a subset can be described. Oh my god, shut up. Just ignore me. Just keep going.
No, I feel like you're onto
Oh,
something.
go ahead. Go ahead. Do you have a question? Maybe?
No, I don't have a question. Just it's okay.
Okay, cool.
I had a thought. Maybe a first.
It's okay. We'll wait for you to formalize that. So basically, it's really easy for us to define like a bijection between strings and natural numbers, right? And we know that all Turing machines are basically strings. So that's where we got the observation that Turing machines has size infinity 1, which is the same as countable natural numbers. So what about languages, right?
Languages are sets of strings.
Yes. So languages are
Wait, sets of characters? Sets of strings.
they're like, yeah, sets of strings basically.
Think of sigma star as basically like the entire set of all strings that you can produce from 0 and 1.
Yeah.
Because
Yeah.
the sigma star. Yeah, I think it depends on the alphabet. The source code for sigma star, which is I think something like sorry, it's just like you can repeat as many things as any combination of zeros and ones, and you define your alphabet as 0 and 1. Yeah. But like if it was like something else, then it would be any combination of like the things in the language. Yeah.
Okay. So we want to show that the number of languages is not the same as the number of Turing machines, right? How are we gonna do that? Any ideas? Any memory from class? Yes, Georgia?
For each string in the universe,
Mm-hmm.
which is the size of the set of natural numbers, you have to make a decision about whether to include the string or not include the string in the language.
Yeah, before that, let's begin with something simpler. Suppose not.
Okay.
Proof. Yeah. So suppose not, then we must have a bijection, right? We must have a bijection between the languages and natural numbers, because we just proved that Turing machine and natural numbers have a bijection between them. So there must be a bijection from languages to natural number. So what does that mean graphically, right? Mm-hmm.
If we wanted to simulate an enumeration of every possible language, we could do the technique where we tabularize strings and languages. So you list
Yes.
the languages that is infinite, and you list the enumeration of strings.
We could list the list of languages, labeling them 1, 2, 3, 4, 5, and so on, because there's a bijection between the languages and the natural numbers, right? So our assumption that the size of languages is actually countable give us this labeling. So we're gonna use it. And what were you saying was?
And then the next, all the columns are going to be strings, and then every point on the grid is going to represent membership of the string inside the language.
Mm-hmm.
Zeros and ones.
And for convenience, we're gonna literally just define the permutation of string. You can define any permutation of string as long as it permutes the entire sigma star. It just means the ordering, right? So if I have a set of like 0, 1, 2, 3, I could permute it as 0, 1, 2, 3. I can also do 3, 2, 1, and 0. I can do like 0, 3, 2, 1. As long as I just count each element once, like list them once. And they are fixed at a certain index. So there's like a specific ordering to a permutation. So what does the entries mean then? Now we have this little beautiful table. Because we know languages are basically like what strings are inside me, right? Yes?
Each entry will be whether the string is a member of inside a language or not.
Yes. So if I ask you what x22 means, what?
Whether or not it's accepted by all.
Yes. So actually, let's do x1 too, because I don't want to mix up the index. So what would x12 equal to in this case? Depending on the language.
Well, if S2 is an L1, then
Mhm.
L1.
Mhm. And otherwise, it will be 0, right? You can flip these values. It's the same as long as you clarify what you meant by it. I can do like x12 equals to 0 if s2 is in L1, it's the same. So in general, xij is equal to 1 if what?
If SJ is ownership of LI.
Yeah, exactly. And vice versa, right?
And not an element.
Yes. Perfect. Now we have a very comfortable representation of all the different languages. What do we want to do? What do we want to do to try to establish a contradiction that this table cannot represent all the languages? Yeah, exactly. We want L not in the list of the table, right? We want L to be not within the set of LIs, where LIs are here, right? So how might we approach this problem? Because there are infinite languages. We can't just look at every one of them, right? Yes?
We use Cantor's technique.
What is Cantor's technique?
You take the diagonal across that table anywhere,
Mm-hmm.
and then you flip every entry, every table entry, that is, and form a language based on the inverse. Then it's impossible that the language could have ever been enumerated as a language, and thus we cannot have an enumeration of languages.
Great. But what if I do not want to use the diagonal?
Don't want to use the diagonal.
Can you give me a language that doesn't use the diagonal? Yes, Marsha?
Maybe X1, 2, X1, 3, but then it sort of also uses the diagonal. So it goes like that, and then it goes like X3, 3,
X,
4,
what did you say?
1, 2, 1, 3, and then 3, 4, 3, 5.
Okay, so here's a problem, right? This corresponds to S1 in the language.
Oh, I meant like the inverse.
Yeah, I mean, let's just look at this. So these two entries are meant to eliminate L1, right? So say my L1 is equal to 0, 1, 0, 1. This is my x12, this is my x13, and your L is equal to something like that. So it starts with 1's inverse is 0, 0's inverse is 1. So you might actually have L equal to L1 here, right? This is x11. As an example, if my L1 looks like this, right?
And like one of them inverse and one of them back.
Well, again, I can still define another L1, like 0, 1, 1, 1, right? Then you literally just go to 0, 1 again, your first two entries, right? So this one doesn't necessarily work, but I think we're on the right track. So what is making, like, what is screwing us up from, yes?
We're looking at two entries from the same language, 1, 2, and 1, 3, both correspond to entries of L1. And the way that the diagonalization, the reason it works is because when you go diagonal, you change your string and your language such that whatever language was on diagonal preceding it must be different from the next language.
I mean, I can still add new languages, right? Instead of looking at x22, I could have the x23 flip in my language. And that's still gonna work, right? We're just looking at the first two entry right now. And we could literally like go like to like xi and then look at L2. Yes?
You have to make it line up with L1 because right now you're comparing x11 to x12.
Yes. Exactly, right? So see how x12 was corresponding to s2 instead of s1 in this language?
Because now you can't. So if L1 starts with x11,
Mm-hmm.
and your new thing that's saying this is not equal to any other one.
Yes.
So x12 is the opposite of what x12 is.
Mm.
Okay, it's the opposite of the second one, but what about the first one?
Yeah, so
it could still be the opposite of x12 could
Mhm.
still be the same as x11.
yes.
But then why does
So what we want to do with the diagonalization argument is basically find a string from each language. If language I contains that string, our language should not contain that string.
But then why does
Right.
the diagonal work at all? Like for example, if we take x1, like the inverse of x11,
Mm-hmm.
and then that could be x12. So like, why does the argument even hold for that solution?
So if I tell you that S1 is in set 1, but S1 is not in set L, do you agree with me that S1 and SL cannot be equal? Right? So that's exactly what we're doing here. By flipping X11 in the original diagonal language, we are telling ourselves that S1 is not in my SL. It's not in my language.
Then why does this not work? Like the two beside each other?
Because instead of having this argument, you're telling me that S1 is in S1 and S2 is not in SL. But it could be very much possible that S2 is not in S1, right? So if my S1 is like epsilon, my SL is epsilon as well, right? Then it's true that 0 is not in SL. It is true that S2 is not in SL, but we still have SL equals to S1.
No, that totally makes sense. What doesn't make sense is like if we flip 1, 2, and then we also flip 1, 3. Like, why would that mean that the
So what this means is, okay, so what these two entries give us is S2 is not in the language L, and S3 is not in the language L. And what this gives us, it's, oh, well, yeah, it doesn't have to be like not in the language L. So if S2 is in the language of 1, then S2 is not in the language of L, right? Mm-hmm.
I can like show her,
Yeah, sure.
and we can like, because I think we should do the recursion thing.
Yeah, that's true.
Yeah, sorry.
Okay, so let's just instead give another language that actually works by trying to match the index of L's and like S. Okay, so what's another language that's gonna work that's not equal to L diagonal? I can start. So if we look at this language, does it work?
So just taking like instead of one string, it's taking two
Mm-hmm.
for each line.
Yes.
Yeah, I think that should work.
Yeah, so how are we gonna prove it? To start the proof, we want to start by suppose not, right? Then exist I such that L is equal to Li, right? Then if we look at string I, it's literally the same proof we did in class because this language is easier. If we look at the string as I, then what? Well, as 2I, sorry.
Wait, what does 2i mean? Is it like S2 and then I is any number? Or is it?
Because now we're trying to prove it by contradiction.
Yeah.
So you're assuming there is a language mark that's indexed at I that's equal to L. So we are trying to prove there's an Li that's equal to the language represented by this string.
Or what does like the 2i index mean?
It means 2 times I. Because right here we're doubling, right? So if I'm looking at language 3, I can't just say, okay, string 3, because that's actually still referring to some language in L2, right? So how are we gonna try to finish this contradiction?
So I guess we can just look at what it is in Li.
Mm-hmm.
And so suppose it's in Li,
Mm-hmm.
then if we look at any like S2i, I guess,
Mm-hmm.
then we actually just did the bar operation on it.
Mm-hmm.
And so it can't be in Li.
If it's in I, then my xi to I is 1, right? But we know that in L we're taking the inverse of it. So it's actually not in L, right? And vice versa, right? Yes. So any questions on this? Yes.
So is the reason you did this double sort of diagonalization technique instead of the original diagonalization because you find it simpler or because it illustrates something else that is important?
It illustrates the importance of matching the string index. What you're trying to do is basically match up the index of the string which with the actual location of your like x in your new language. So if this is the 6s I have, like 6s x in language L, I can mark it like, right?
Then you'll be able to find that one member that disagrees.
If I call this member L6, I want this to have like a relationship with the string that's S6, right? So it could be very much possible I just have a bunch of zeros at the front, and at S6 I decide to take the inverse of x14. Well, this is 4, yeah. At S4 I decide to take the inverse of x14 and I go diagonally down there. That also works. Because you can always find a string SI from every language that gives you a contradiction. Does that make sense?
That makes sense.
Yes. Okay. Let's see. Diagonalization. We'll skip the self-hating Turing machine because that's already on class and you can go review your notes. But let's look at self-reproduction. So now we want to have a machine that basically reproduces itself. How are we going to try to approach that, given that my machine cannot print my own description?
Maybe before like you go into the construction, can you explain like the rationale behind like why you want to do this?
Because we want to be able to describe ourselves from within the machine. So if you have a machine M, this is literally like the foundation of all the contradictory proofs we will develop for undecidability and unrecognizability. If I have a machine M, before I finish constructing M, I want to be able to use my own description, right? I want to be able to set beta to my own description without even knowing what my description is. Now that sounds really impossible, right? That sounds like self-contradictory and insane. But recursion theorem guarantees that, yes?
I just want to clarify.
Mm-hmm.
The reason why this is me also asking to make sure I understand. The reason why we need our own description is that so that we can run it in the decider and recognizer to manipulate it, right?
You don't necessarily need to run yourself in the decider. Well, yes, you want to use this as an input in your decider or recognizer.
So that's like the basis of why we want our own description.
Yes.
Repeat that again?
We want our own description because we want to be able to throw our own description into a decider or recognizer for contradiction. Yeah.
I don't remember the full proof, but I know that we're going to need 2 tapes at some point, and so we'll have to simulate 2 machines running. Even though it's only 1 machine.
Okay. So do you want to get us started?
Let's define 2 Turing machines, A and B. Each has its own tape, and then we can also take a look at the pseudocode that's driving both of their actions.
Why don't we just let them work on the same tape?
Okay.
We can do that, right? We can easily have them print to the same tape. Imagine like 2 programs writing onto the same txt file.
Okay, so we'd start on A, and let's set a variable equal to the description of B.
Okay.
Can we do that?
Yeah.
Okay. So we can't get our own description.
Yeah, but we can look at other
we can say we
machines'
can take
descriptions.
the input of B. And now that we have that, we want to put that onto the work tape. So print alpha to work tape.
Yes. So instead of having this extra step, is it possible if we just print the description of B?
Yes.
For simplicity, yeah. So for simplicity, we can skip setting an internal variable and just print the description of B because we can get it from the outside. Okay, so now we have a description of B on the works tape. What do we do next? So whatever is in this box is printed on here by A.
So part B will take that description of B
Mm-hmm.
to new file.
Yes. We can read from the work tape. We can't read our own description, but to us, the work tape is always just a set of string. It's literally just a string. So we can set alpha to be the content on the work tape, right? So now we have alpha. And what do we want to do next? Our goal is to get the description of A and description of B onto the work tape. And the description of A is what's inside the box. It's literally a string. Yes?
Since we can have a Turing machine that gets another Turing machine description, we could inside of B get A's description and set it to a different variable.
Actually, that would cause a problem, right? Because when I'm trying to print B, I have to know everything B has. But when I'm reading through B and blah, 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 I have a lot of lines, and suddenly I realize, oh my god, there's something that wants what I have. I will have to look at my own description, but that's not allowed, right? So we can't directly access A's description in B, or else there's going to be a loop. Do you understand why there's going to be a loop if we directly say print A's description? Oh, sorry.
No.
Can you come up with like an example, like for example, like program that will like show that you can't do that?
Okay.
In class we use like print.
Okay, so, do you want to come up with a Python example, maybe?
Sure.
Okay. Do you want to write it?
Yeah. All right. So if basically the idea is if we set A equal to B, and then we set B equal to A, and then we're trying to define something, like if we put like a print statement in there, then it's like, okay, what does A do? Well, it does what B does, and B prints. And now, what does B do? Well, B does what A does, and A does what B does, and that prints.
Yeah.
And it just kind of keeps going. So it's like,
Actually, let's not do print. Let's just call the function. Let's just have a function that calls function B and function B that calls function A.
like A. Which says print whatever the content of B is. And let's just say this calls B. And then if A is printing B, and then B references A.
So imagine B and A as two like small functions, right? Because I can print function f in Python, right? So when you are trying to print B, when you reach this point, you are jumping to function B and you are trying to print whatever B is. However, to get B's content, you have to jump back to function A and get what the content of A is.
But I said
Mm-hmm.
you have a variable that is equal to A.
It's the same. Instead of printing f, I can say alpha is f, right? But this function, you have to call it. You have to still go into the function and figure out what the function returns, right?
Imagine if in addition to these print statements, there's also something that said like print hello in both of them, and then you print hello, and then you call the next function. That function calls the original function, and then you. It makes sense. You would just infinitely print hello.
Wait,
I think that
I have
explains
the
a little
marker.
bit better. Yeah, take that back.
So instead of printing, let's just do function calls. So let's define a function as f, which just calls g. And let's define a function g, which just calls f. Now what would happen if inside main I call function f? Is this program ever gonna terminate?
If you had inside of definition G, if you had x equals,
X equals.
would that
But this is not a string. This is a function. You have to run it to return a value, right? I kind of get what you're trying to say. You're saying, what if we just have this as a string, x equals to f? However, the problem is we don't know what our selves are. So when we're trying to say, I want this to be a string of f something, I still need the content of myself, which I don't know at this point yet, right? It's like the print example. You can print, comma, like you can do like print inside the function, and your output is just gonna be a single print. And if like even if you add more prints, your output is still only gonna be this part. That doesn't include the last print you're supposed to include in the output. So we're trying to get around this issue. Like, you see how there's one less print in our output than the original function? So that's an issue we're trying to get around. Do you get that? Okay, sounds good. Now that we've settled that we cannot directly get A's content, what should we do?
You can't directly get A's content, but you can like recreate it. And I
Yes.
think the difference within lecture was we were saying in lecture like we kind of guarantee in B that we're not gonna touch anything in A. Otherwise, if A prints B and B also gets A, then you have like that circular dependency, right? So instead of like directly trying to grab A's description, I think what we did in lecture is we were like reconstructing it using what's on the work tape. So
I know that A is trying to print B.
Yeah, so A is trying to print B, and so the description of what it does is just print B. So if you just take that description, that whole thing is just description of A, and that gives us like bracket A.
So do you want to continue down? It's okay. You can say I'm gonna write with you.
You'll just have a new variable that is the string print alpha,
bracket, just for clarification.
And then to get A and B on the work tape, you can just have all of that moved to the beginning of the work tape.
So we're trying to append beta to the work tape, right?
Yeah, or like prepend, I guess.
Oh yeah. Sorry. Now, realize that when I prepend beta, right? When I created beta is literally the string print b. So when I prepend beta to it, I get, where's my other functioning? Print b and b, right? Because this last b comes from the work tape content. This is the prepended beta. And what does this look like?
That's just the description of A.
Yeah, right? That's equal to description of A and description of B. So we're actually able to print our own contents onto the work tape through some extra machines, like an extra layer of machines. And yeah.
Is it kind of like when we switch from DFAs to NFAs, we start taking a lot of like liberties on definitions of NFAs. It's kind of the same thing here when we're always imagining like multiple tapes, multiple machines within a machine. Even though certain machines can run other Turing machines as subroutines, that's not what we're doing here. It's we're just simulating two separate machines as subroutines on a Turing machine, but we're building one machine.
Yeah, it's like how the equivalence of multi-tape Turing machine was the single-tape Turing machine. Like, if you spend long enough on trying to construct these machines that are equivalent to each other, you can. It's just that that's not the main focus of the class.
Yeah, it's just annoying.
It's more on like pseudocode level. So I remember Professor promised that he's not gonna have us draw a Turing machine on the final because that's gonna be miserable. So yep. And this proves that we could make use of a machine's own description from inside itself. Yeah, that's basically the recursion theorem. And do you guys want to go into undecidability and unrecognizability? Okay, sounds good.
Elliot, maybe if possible, like using your expertise, how do you think like the exam problem will involve the recursion theorem, if any?
This is literally, you're literally always gonna call this line at the beginning of all the machines you're trying to construct.
Yeah, but the professor also made sure, even like the TA said that like make sure we know how to prove the recursion theorem.
Oh, okay.
So I don't know the answer to this as well, but like maybe you have like a guess.
Well, other than just building it off raw, maybe they could ask you like how does it work, explain how this process is, or it could be the idea of two like interrecursive machines working alongside each other, because you've seen like interrecursion, right? Instead of recursing on yourself, you recurse with another machine. Like in Haskell, we usually use two different functions that call each other that can tell you, like, for instance, in Haskell, if you want to determine even and odd, you can call n-1 on even function. And in the even function, you can again call n-1 for the odd function until you recurse down to 0 or 1. So like functional programming, that type of content.
You could also just make any tweak to a Turing machine. All right, now does our method work, that sort of thing.
Yeah, also possible. Like they could have a new type of machine called magical machine, and prove how magical machine can print itself. Yeah.
That could be a good idea. Thank you.
Yeah. Okay. Undecidability. Everyone's favorite language, loop. Ugh. Oof. This is not coming off. Bruh. Ugh. Also, feel free to grab some candies if you want.
Oh, I'm helping myself.
Yes, yes, yes. These are purchased by our. These are purchased by our amazing logistic committee. Free candies. Let's go.
I didn't take anyone.
Is there something from the practice final that uses undecidability you want us to go through?
I can do an example.
Okay.
Can I write on the whiteboard?
Yeah.
Oh wait, maybe you should like define what decidability is.
Yeah. So, decidability instead of undecidability. What does decidability mean? Yes?
Turing machine is a decider for a language if for every member of the language the Turing machine accepts, and for every string not in the language the Turing machine rejects.
This is for all statement. This little symbol is for all, by the way. This is like not in. And the decider will never loop. That's a very comfortable property we can make use of. And what about recognizer? Yes?
For all x in L, m of x accepts. For all x not in L, m of x rejects or loops.
Yes. Does not accept. Let's just say does not accept. So it could loop or it could reject. Either way. But we know for sure that if I give this Turing machine a string in my language, it's gonna accept. Like it must accept if it's in there. Now, really? Okay.
Could you go over the relationship between the two and
If it's decidable, then there's definitely a recognizer for it, right? Because a decider is very clearly a recognizer. If it's and if we apply contrapositive to that statement, so for statement 1, like if I have a statement alpha implies beta, then by contrapositive I know not beta implies not alpha.
but that doesn't work for
It works for every logical statement. We have a statement that if a language is decidable, then it's recognizable. So what's the contrapositive of that? we have a true statement that if my language L is decidable, then it implies it's recognizable. What's the contrapositive of that?
If it's not recognizable, then it's not decidable.
Yes, that's the relationship. Yay, Rin, your turn.
No, I'm not the best at this, so
I believe
have
in you.
Guys, help walk me. Can I miss that?
Yeah, sure. Time to sleep. No. Oh yeah, sure.
Thank you. What do we do with this?
You clip it.
Here. Oh, thank you.
Bruh.
What? Thank you. Let's try to prove the undecidability of the language L prime, where the definition of the language is for every machine M, Lm is all prime numbers. And remember that for decidability, M decides L, if for every X in the language, M of X accepts, and for every X not in the language, M of X rejects. We do not look at the loop case. All right, what is the first thing that we do? You do get a candy. And what does that mean when we prove like the opposite?
That means there exists a decider.
Yes, there exists a decider D for L primes. Let's build a machine that will do this. And within the machine, we declare a variable called x that takes in it as input. All right, what is the next thing that we do?
We get our own description of M, and we end up running that on our hypothetical decider.
All right, I'm going to call it let alpha equal to m, where it is our own description, and then we will run our decider on alpha. Now, what are the two cases that we have?
Accept and reject.
Yes.
Thank you.
Accepts and if rejects. And what are going to be the two results of the cases that we do? Yes?
But if D accepts, then it is under the impression that M is a machine that has a language that is only prime numbers. And so in order to make sure this is not true, we just take a prime number and accept it inside of M. Or a non-prime number, yeah.
Yes. So we take the language that accepts all primes. But because
Then that's still true. If you don't accept anything, everything you accept is still like it's vacuously true that everything is prime. So mathematically, if Tokyo is the same city as Paris, then my cat can fly. This statement is true. It's vacuously true. The like precondition, the premise is already false.
And then like in this case, if we said that reject everything.
If we have nothing, then we have all prime numbers.
Oh.
We have nothing.
I think you could say like reject of prime number, then that'll make sense.
Yeah, because I'm saying.
Instead of like all.
Wait, does it reject all still work?
No, because I thought it would work because I thought that LM has to accept all like LM has to hold all the prime numbers, but not like we're checking that it holds all prime numbers. I feel like there's a difference, right?
So
There's a
if-
weird little like
Yeah,
semantic.
there's a little semantic difference between like does LM have all the prime numbers or like does it have all like
Only
does
prime
all the prime numbers in the world? Like
So
there's
if
a
you
difference.
see like this is all prime, it means if I take element A from the set L of n, then A must be a prime.
Yeah, but like what I thought is like it's checking that is this language a language that it accepts all of the prime numbers.
Accepts every single prime
Yes,
number.
exactly.
So there could be some B that is a prime number that isn't in the language,
And then the
But-
language would not work.
but L
Yeah.
could still accept. But in this case, I think it's just every member of the language is a prime number.
I
Yeah.
mean, there are different ways you can interpret the statement.
Yeah.
Because like
Was this amazing?
grammatically, both are true. Both
Yeah.
are correct.
Yeah, it's just
Is this
I've
amazing?
interpreted it another
Oh,
way.
the practice one?
Yeah.
No, I think we're just like discussing that. So
Okay.
What?
Yeah,
like
I
this
think-
example, that's not from a test or something.
I don't know. I haven't looked at the practice.
Yeah, me either, bro. Maybe we could practice final actually.
But we did
There
it
might be
for
some
actual
interesting questions.
And if it rejects, then we could, then it's under the impression that L is, that M is a machine that has all prime numbers, and, or if it believes it is not that, I'm not sure how to get a contradiction here.
Well, if it oh well,
If it rejects,
then it means that it's like
Wait.
not all prime
so
numbers.
is all prime numbers mean that L of M is like every prime number?
Yeah, should be.
Oh, okay. It doesn't mean that it's only prime numbers, right? Just that it's every single prime number?
No, the
No.
opposite. I think. Like
Oh.
this statement, I think, means that in a set of numbers inside of this language, whatever those numbers are, if there are only prime numbers, it doesn't matter if there's like every single prime number in the world, but if there's only prime numbers, then it will work. I think that's what it means.
Okay, let me go through the second like case as well. So case 2 is where D rejects, meaning that the language is not all prime numbers.
So that means that there's at least like one prime number.
That means that M would accept X if X is prime. Therefore, L of M would equal to all primes. But that's a contradiction.
I don't get it.
And then this condition would be accept.
That could work in the world, or
Yeah.
That could still work.
that's what I thought initially, but they told me that it's not like what they mean. They mean like
No,
I guess it works
case
either.
1 that's not true, but in case 2 that's true.
I don't understand like the reject statement. Like why would
Elliot, can you take over? Okay. Thank you. Okay, Marsha, let me ask you a simple question. If I alternate my input, is it ever possible that by changing my input, I'm going to change the result of B on alpha?
no.
No, right? So you agree that we're ever going to be ending up in only one of these cases,
Yes.
right? Okay, then we're going to divide it up to 2 possible cases for discussion. So it is like, it's obvious that either we end up here or here for every possible x
Yes.
when we run machine on x, right? So suppose we end up at the accept case. So it
I
never-
understand the accept case. I don't understand the reject case.
Okay, so suppose it always ends on the reject case. So B on alpha always rejects, right? So for all the x, this is the only criteria whether we're gonna accept it,
Yes.
right?
we accept all of the x's that are prime.
So what does that imply of our language of M?
That it's all prime.
Yes. So it does satisfy that language is all primes. So the description of them is actually a part of L prime, right?
Oh, okay, yes.
But what does our designer tell us?
That it rejects, so it tells like, oh, thank you. That it's not prime. Yeah.
So it's not a language, but it's still a language in L prime. How can that ever be true, right?
Yeah, that's a
So that's impossible. So this proves why this is undecidable. Yay, thank you, Rin. Okay. Now we have seen an example in decidability.
So when we're building M, I just wanted to clarify, what is the M? Is it like a language that we're testing?
M is a Turing machine.
So we're just constructing a whole new Turing machine.
Yes, we are constructing a Turing machine where we can use the decider inside of it.
So you know how we would use the decider to test if the language is prime, L prime. So in this case, are we like manipulating that hypothetical machine? So are we manipulating the machine that we want to test, or are we just creating a completely new machine?
This is the machine we're testing.
Okay, so whenever we build M of X, we're basically reconstructing the machine that we want to test.
Exactly.
Okay.
It's like if you think of the decider as like, all right, we assume it works. We don't know it works, but we're assuming it is for the sake of contradiction. And then we build a machine that helps us build that contradiction in every case, so that it's just not possible to exist.
Because for the decider to fail on that like language, it has to fail for at least one machine, right?
Yes.
So we're
exactly.
making like a rebellious machine.
Exactly.
That is like a abstract machine that we use to test.
Yes, because we're trying to prove the undecidability of a language by first assuming that it's decidable. If it's decidable, there must exist a Turing machine that's a decider, which takes in a description of a machine and outputs accept if the machine has its own language equal to this. And it rejects if it's not equal.
Okay, because sometimes I get confused where like.
Yeah, it's very confusing. So I will always tell myself M is a Turing machine, but if I add a bracket around it, it's a string. So, oh, thanks. It's a string, and I can use it as an input to another Turing machine.
Because recursion is super confusing.
Yeah, I guess like the part that I get confused on is like we use M in the description of L prime, and then we also use it when we are building M.
Oh no, these are two. Okay, this is a general symbol. Okay. Yeah. Okay. Okay. Let's just say n, right? This is a new machine.
Okay.
Yeah, in mathematical symbols, this is like inside a Python function, you can have a variable called a, and outside of that function, you can still use the same symbol to represent some completely different values, right?
Yeah. So
Yeah.
in an exam or like homework, if we were to use M where it's like in the description as well as what we're building, do we have to clarify that like those are two different M's, or is that just like assumed?
Oh no, you don't have to clarify. This is general. This is just a general Turing machine.
Wait, that makes so much more sense now.
Yeah.
I was also confused.
Yeah, no. This is about like mathematical formality. So, yeah, if you go take some like proof classes, I think it's gonna be really helpful for formalizing and just like reducing the confusions. Yeah, try it. I think like the undergrad multivariable calculus honors version has a whole ton of proofs. It's not too difficult. It's not an upper div. It's still a lower div. So if you want, you can take that. Okay, let's move on to recognizability.
Wait, so this M in like build M
Mm-hmm.
and alpha, the
M in bracket is a string
Yeah, but like string of the itself.
of the machine we're building. It's a string describing the machine we're building. The canonical description.
So like if we took all of what you wrote and that would be a string, that is what it is, right?
Yes.
But is it? Yeah, but isn't there like another M inside the
Yeah, that's exactly what recursion theorem is about.
Yeah,
We are able to get our own description through the recursion theorem.
It's like if you kind of as a machine knew your code and then were able to use that to like modify something.
Because in the recursion theorem, it's A, B, and T.
yeah.
So,
So the
yeah.
T part is basically what we're building as M. So the A and B is implicitly there. We just didn't write it.
Oh, I see. Okay.
Yeah.
Okay, thank you.
Yeah.
Yeah, that's so confusing actually to like wrap around your head, but it's like on like an intuitive level you get it, right? And like the logic you get, but then like you think at the base of it, it's like
Yeah, so whatever Turing machine you have down there, you're still able to like just print it in A and use the same trick. Okay. Recognizability.
Ellie, you mind if I give us a quick introduction to recognizability?
Oh yeah, sure. So here you go.
Thank you.
Mm-hmm. Where?
Give the cap to the gentleman.
Somewhere. Somewhere.
Alright.
It exists.
I feel like I didn't really understand recognizability and unrecognizability until kind of recently. When we were first introduced to recognizability, Professor Sahai mentioned one language that it was like trivially easy for, if anybody remembers what it was. He said it's not even like worth writing on the board, it's so trivial.
Accept everything.
No, it's the halting problem.
Oh, okay.
So
Oh yeah.
Wait, quick question before we move on to recognizability. So to prove something is undecidable, we do the contradiction, recursion theorem, so on. How do we prove something is decidable? Is there like a specific?
we have to build a decider.
You build a decider.
Such that
That's basically it.
such that we don't break any rules of Turing machines. And if we can do that, then the decider must exist. But for recognizability and the halting problem, if halt, which is really just a language,
Danny, give the mic so that the recording people can also hear you.
thank you, doctor. How's that?
Yeah, that's good.
So the halting problem, if I can find a good marker,
there was a black good one.
that's good. All right, halt. So it's all machine descriptions such that for some x, m of x halts. And the reason that we call this vacuously true is we are going to try and build a recognizer for it. So if we want to imagine this hypothetical recognizer, we would just build it like by construction.
Sorry, Danny, what is this little squiggly thing near M?
This?
Yeah.
Oh, that's just supposed to be the token. I've never written on a whiteboard before. This is harder than it looks. Like
I'm sorry.
the machine
I'm
description.
sorry, I didn't see it. I'm sorry.
And so for our input, our recognizer would take any machine and any input. And And if it's a recognizer, then there's going to be 3 cases. Case, accept, case, reject, and case loop. So this is a little different than proving unrecognizability. So we're not necessarily looking for a contradiction. We just want to show how each of these could work and why it's viable. If we get started with our accept case, that means that the M that is fed to R accepts that X. So what would we want to do to show that this is true? Anybody have any ideas? Nika?
Just to, so in these scenarios, are we accepting and rejecting, or are we halting and saying does not halt?
Well, we're just imagining what this recognizer could do.
Okay, so if it accepts, that would mean that it is a part of the language of halting.
Yeah.
So it
And
means
so-
that the language finishes at some point.
And so we want to accept, right?
You know, I think that the way that I've described this is a little bit overcomplicated. Instead of thinking about it in terms of the cases, let's just think about what this recognizer could do. So it has the machine description of M and it has an X. So it can just run that because Turing machines can run other Turing machines as subroutines. So if we just run M of X, then we know M of X, because Turing machines can, like recognizers, they can only do 3 things at the end of the day. They can only accept a string, loop on a string, or reject a string. So we know that we can build a recognizer because we know that this machine can only do the same 3 things that a recognizer does. So if sorry if this is way too low. If M of X accepts, and I'm remembering this like for the first time, I've never tried to teach this before. If M of X accepts, then we know that M will halt on some X, and so our recognizer accepts. In the reject case, it's kind of the same thing because a reject is just a form of halting. So R would accept. And I guess where things get sticky is the loop case, because if anybody remembers, if we have a loop, then we can't put in any sort of condition after that because our machine's just looping. We can't do anything about that. And so in this case, if M of X is looping, that means R is also looping, which means that M can't be in the language because it doesn't halt, which is okay. Yeah. I like this as an introduction to recognizability, but that's all. If anybody has any questions.
One little question.
Mhm.
Is that okay that we're doing from the perspective of like if M does something, not if R does something? Like, is that okay?
If M does something but R doesn't do something.
Because I remember in all of the cases that we've done, we like run R, and then we do like if R accepts, if R rejects, and if R loops. And in this case, we kind of did the opposite. We did like if M accepts, if
Yeah.
M rejects. Is that okay? Like
It's okay because we're not doing this machine or this language isn't unrecognizable. That the reason we usually do M first and then use a recognizer as a subroutine is because we're trying to prove unrecognizability, and we're using our M to build a contradiction that makes sure this can't exist. But in recognizability, we want to build the recognizer and show that it can always work.
So this kind of like shows that this halt is recognizable, and this is how we prove it by building the recognizer.
Yes.
Okay.
Like by construction. Usually anytime you want to prove decidability or recognizability, then you want to build a recognizer or a decider. And the reason we put this machine in is just because we know that Turing machines can run Turing machines. And that's like, it's kind of our only option because we just have this recognizer. We don't really know how to define it, but we know we have an M and we know we have our X, and we want to figure this out. And so you build the conditions to suit this.
I feel like I might have a
What
comment
up?
that could help there. To your right, if you point at run decider of alpha.
Where?
Below. Yeah. As opposed to being a decider, we're doing a recognizer, but we're basically zooming into that run right here.
Oh, okay. Oh yeah.
Kinda, because we're not putting the decider inside of a machine. Well, we do put a decider inside of a machine here, but here we're not putting it inside of a machine. We're putting a machine inside of the recognizer.
Yeah.
Exactly.
So like if M loops, that means that the whole
You want to throw that so bad.
then the recognizer will also loop, right?
Yes, everyone did great. I don't want to take up too much time. The other Daniel's smarter.
Oh, thank you, Daniel.
Good job, Danny.
Can you pass the mic to Daniel?
Of course.
Daniel.
Danny to Daniel. Okay. Yeah. So, what I kind of wanted to go over now that Elliot's covered most of the other top. Oh yeah.
Sorry.
Question.
I just had a question about the triangle scheduling because they mentioned
Yeah.
that would be important. That is used to prove something is recognizable, right? Or is it used to be proving something is both unrecognizable and
I forget. I think in class when we used it, it was recognizable. Prove it's recognizable. I think it was like, prove the language, L, L like non-empty, I think, is unrecognizable, or recognizable, sorry. And non-empty just means all machines where the language of the machine is not empty.
So could we use triangle scheduling to prove something isn't recognizable?
To prove it isn't recognizable.
Or
Well,
is that strictly just a recognizable kind of proof?
for proving it's unrecognizable, usually the proof is suppose not, and then you try and like run your recognizer. So I think in that sense, we haven't really seen cases where we would like do something different to just like building a machine for proving unrecognizability. Yeah, I think it makes more sense for proving recognizability because in that case, we kind of have to like make our own machine and also show that it works on all strings. So the triangle scheduling is like how to schedule all of our strings.
Okay, and the reason why I asked was just because they keep emphasizing how important it is for the final. But we've only seen it in like a super simple example, such as like
Yeah.
non-empty.
Yeah.
So like, I can't imagine that on the final we would have to use it on a simple
Yeah, that is tough. I don't have a ready example right now, but maybe if I come up with one, I'll like post it on Piazza or something. Yeah. Uh-huh. So, kind of what I wanted to go over now that we have all the concepts is two like parts of problems from the winter 21 final, the practice final. And I thought these were like pretty helpful for thinking about Turing machines. So the first one, let me see if I can find the actual problem part. This is 4A in the winter 21 final. It's called Oracle machines. So the idea of an Oracle machine is the same as a Turing machine, just that I won't go into detail about what the description says because it's like a page long, but essentially all it's saying is that you get an extra operation that returns a 1 if the language of your machine has an infinite size and returns a 0 otherwise. So language of the machine is less than infinity. And in this case, like the specific infinity, countable versus uncountable, doesn't really matter. We're just like saying they're all the same. So as a quick example, like something that could be infinite size is like, let's say the machine accept all. And in that case, L of M would just be like every string, right? That's pretty infinite. And then something that isn't infinite, let's say like the machine that only accepts 0. So then